Hello and welcome. Let's talk about our ICRA 24 paper entitled Learning Self-Confidence from Semantic Action Embeddings for Improved Trust in Human-Robot Interaction. So first, why are we interested in trust in HRI scenarios? One of the main reasons is because it affects important aspects of the interaction, such as task success or interaction quality. A broad range of trust antecedents have been identified so far, and a lot of research is focusing on how those factors can be controlled to affect trust, and through trust, the outcomes we care about. In our case, we focus on one of the predominant factors, observed proficiency, or in other words, how often the robot is seen succeeding or failing. Now, how can we control this? We identify three main ways: failure detection, failure recovery, and failure anticipation, which is the one we're focusing on. So in short, our goal is to enable the robot to predict an action success probability before it attempts that action, so that it has an option to ask for help or to adjust the way it's going to execute the action if necessary. So let's have a look at how we achieve this. Our architecture is called SCONE, meaning self-confidence through observed novel experiences. We focus on collaboration scenarios where both agents have access to a set of text instructions, a recipe in our case, and a list of perceived affordances in the environment. In our application, this is achieved by combining object tracking class names with a simple rule-based system, but there are other ways to achieve it in the literature for more complex scenarios. SCONE relies mainly on three components. First, the embedder takes text instructions and textual descriptions of affordances and projects them into a common latent space using a language model. Second, the instruction filter predicts the relevance of one instruction overall. This has no impact on the self-confidence aspect, but it allows us to improve the recipe following performance. We filter out instructions that are irrelevant to the robot, such as enjoy the meal in a recipe. After this filtering, cosine similarity is used to find the most relevant affordances for each step. And finally, the self-confidence predictor uses the same embeddings to outcome a success probability based on previous interactions. By combining both scores, the robot chooses relevant, feasible actions first. The action outcome is then observed and used to update the self-confidence estimator. To evaluate SCONE, we want to address three questions. How fast and efficient is the learning process? How relevant our embeddings are for instructions following? And how does this learned self-confidence impact human trust? Let's have a look at the learning process first. As we've seen before, our framework relies both on embeddings and on a self-confidence predictor for its outcome, and both will impact the learning performance. So here in the results table, you have on the left different types of embeddings, like one-hot encodings or GLOVE or transformers, and in the first row, different types of predictors. Come back to that. For the evaluation, we collected datasets from simulated and real-life setups with different proficiency profiles by inducing on purpose some errors in the process with different frequencies. Each dataset consists of 100 actions and their outcomes, and we used a custom metric to capture both prediction quality and learning speed. We evaluate the model's accuracy with training sets of different sizes, and then use the area under the curve to capture both how sample efficient and overall performant the model is. We averaged the results on all proficiency profiles for each embedding/model combination, and the results are summarized in the table. The first column shows the results for the best estimator, like GBM. However, we found that some models tended to perform worse than random when trained with very little data. To account for this, we also computed results for models whose prediction was replaced with a random value with a probability epsilon. This is what we call the epsilon greedy condition. This improved the overall results, with K and N becoming the best estimator, as shown in the second column. In both cases, we found that semantic embeddings are good predictors as they capture action similarity better than alternatives. Since SCONE uses semantic embeddings for action representation, it offers a relatively simple solution for instructions following tasks. To evaluate its performance, we used the TastyV2 dataset to generate random kitchen states and manually labeled the relevant actions. We found that pre-trained language models perform reasonably well and even on par with state-of-the-art when further trained on a custom dataset. Finally, we conducted a pilot study with 31 participants to evaluate the impact on human trust. Each participant cooked twice with the robot, one with each condition. We measured subjective trust using the MDMT and TPS-HRI questionnaires, and objective trust through the number of times participants choose to take over from the robot. We used Bayesian statistical modeling to evaluate the results. The contrast plots on the right show the distribution of the parameter difference between the two conditions. Since both distributions are clearly positive, we can conclude that self-confidence awareness increased reported trust. Similarly, we modeled the number of interventions as a Poisson distribution, here in the lower half of the slides, and show that there are an average of 2.8 fewer interventions when the robot has self-confidence awareness. In other words, our results indicate that being capable of predicting their own failures is a promising way for robots to calibrate human trust. Future work will attempt to investigate this effect further. Thank you for your attention.